Let's take another statistic, the variance, and create a sampling distribution of the sample variance. So the sampling distribution of the variance is the distribution of sample variances with all samples having the same sample size n, taken from the same population. So recall that the population variance, sigma squared, is equal to the sum of each random value x minus the population mean squared divided by the population size. And how this was different from the formula for the sample variance. Here we took the sum of each value of the random variable minus the sample mean squared, but here we divided by n sample size minus 1. Okay, so let's use our example of Farmer Fred's chickens and recall that our population size was 3 and the population consisted of 3 days of egg production where there were 5 eggs, 7 eggs, and 12 eggs. That was our entire population. And recall that we computed the population mean to be 8 eggs. So let's calculate the population variance. Okay, let me change. So the population variance will be equal to each different possible value I could select from my population minus the mean squared. So we'll do this. We've got 5 minus 8 squared plus, then I could have 7 minus 8 squared. The mean is 8. We're summing all these differences, and then the last one was 12 minus 8 squared, and all of that over our population size of 3. So let's see what we get. 5 minus 8, that's negative 3 squared, plus 7 minus 8, that's negative 1 squared, plus 12 minus 8, that's 4 squared, all divided by 3. Okay, so negative 3 squared is positive 9, negative 1 squared is positive 1, and 4 squared is 16. And when we add those up, we get 26 over 3, and that I'll go to 2 decimal places for right now, 8.67. And again, this is now in eggs squared. Eggs squared. Remember the units. Now if I took the square root of this, I would get the standard deviation, and it would just be eggs, because the square root of x squared would be eggs. Okay, but we're just dealing with the variance right now. Alright, so what we did last time with the mean, we drew every possible sample of size 2, and let's do that again. Every possible sample of size 2, then we're going to compute the sample variances. So we'll need the sample means, and we'll have our x values in our sample, and we'll divide by the sample size, which is going to be 2 minus 1. Okay, so let's create our samples, and it'll be the same as we had last time. So the samples were, we could draw the day that there were 5 eggs produced with replacement, put it back, and draw it again. Or 5, then 7. I'm going to try and space them out a little bit better so I have more room for calculations. 5, then 12. You remember my pattern, how I did this, and I did 7, 5, 7, 7, and 7, 12, and then 12, 5, 12, 7, and 12. 12. So we had 9 possible samples in our population. That's every possible sample of size 2 that we could draw from this population. Now I'm going to need the mean for each sample because I've got to use that in this calculation here. So I need my sample means. Now we got those last time, so I'm not going to write all that calculation out. Let me see. Let's change. So our means were 5, and then remember this 5 plus 12 divided by 2, 5 plus 7, sorry, divided by 2, that's 12 divided by 2, and that's where we got 6, and so forth. Then 5 plus 12 divided by 2, we got 8.5. So these you would already have. So this one was 6, of course this one's 7, this one was 9.5, and then this one was 8.5, and 9.5, and 12. Those were our sample means. Okay, now we need to calculate our sample variances, our S squared. Okay, so recall what we're going to do here. We're going to take each value in our sample, there are only 2, subtract the mean from that, sum those up, and divide by n minus 1 for each one of our samples. Okay, so the first one would be, we'd have 5 minus the mean, which is 5, that squared, plus, we're summing all those up, here's another 5 minus 5, the value of x minus the mean, the sample mean squared, all over, our sample size is 2, but then we subtract 1. So we get 0 plus 0 over 1, or 0. So the variance for this first sample here is 0. Okay, the next one we'll have 5 minus, now our mean is 6 squared, plus 7 minus 6 squared, again all over 2 minus 1. 5 minus 6 is negative 1, and negative 1 squared is positive 1. 7 minus 6 is positive 1, positive 1 squared is positive 1, and 2 minus 1 is 1. So we get 2 over 1, which is 2. So our second variance is 2. Okay, these are our S squares. Okay, and then let's do this for 5 minus 8.5 squared plus 12 minus 8.5 squared all over 2 minus 1. Okay, 5 minus 8.5, that's negative, I'm going to write this one out, 3.5, be sure we all get it. And then 12 minus 8.5, that's positive 3.5. And this is all over 1. So the negative 3.5 squared, that's going to give us a positive result. So is this one. They're both 12.25. 12.25 plus 12.25 all over 1, and we get 24.5. So that's the variance there. Okay, well, when we had the same values, 5 and 7, 7 and 5, the mean was 6, I'm going to get the same result, aren't I, for this fourth sample? So I'm not going to recalculate that. I know that I'm going to get a 2 because my values are the same, just in different order. So that one's 2. Now this one with the 7s, well, we saw before when the x values were the same as that meant the mean was the same. That meant we ended up with a 0 numerator and the variance was 0. So the same thing's going to happen here when they're both 7. 7 minus 7 is 0. Likewise, we'll have the same result. But here's one we haven't done yet. So let's do that. 7 minus 9.5 squared plus 12 minus 9.5 squared all over 2 minus 1. Okay, 7 minus 9.5, that's negative 2.5. And 12 minus 9.5, that's positive 2.5, all over 1. And these are both 6.25. And we add those up and you get 12 and a half, 12.5. Okay, well, we've done also the one that had the 5 and 12. It's just reversed order, but we had the same mean, so we know our variance is still going to be 24.5. We'll end up with the same result there. So we don't need to recalculate that. And let's see, we did 12 and 7 and had 9.5. We just did that one here. So these two would be the same. They're both 12.5. And the last one is another one where both values are the same, and so the mean is 12, so our numerators are going to be 0, and so our variance is going to be 0. Okay, so now we've got all of our variances, and when you do a problem like this, note the things that are similar so you don't do extra work. There's no need to run through these calculations again if you can see that they're going to be the same. Okay, so now we want to create a probability distribution. And actually before that, let's find the mean of the sample variances. Okay, so we've got these 9, remember we had 9 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we've got 9 variances. So let's find the mean of those and then we'll create our probability distribution. Alright, so the mean of the sample variances I'm just going to add them up and divide by 9, right? So I've got 0, 2, 24.5, 0 plus 2 plus 24.5, that's the first 3. Then I have 2, 0, and 12.5, 2, 0, and 12.5, and the last 3 were 24.5, 12.5, and 0. And I just want to find the mean here of the sample variances, so I'll divide by the number I have. And we end up getting 78 divided by 9, which is rounded 8.67. Recall that when we did calculate the variance, the population variance right here in the purple, 8.67. So we're seeing just what we saw before with the mean, that we're getting the exact same result, whether we use the population or every possible sample of the same size. Okay, now we'll create our probability distribution for our sample variances. So what were the possible S squares? We're going to list those. Then we're going to list the probability of getting each one. Out of 9 possible, how many ways, right? And then we'll calculate our sum of our x times p of x. Okay, so the different variances, well, the smallest one was 0. I could just look here in this calculation, can I? 0 was one of our variances. We also had a 2. We had 12.5 and 24.5, and that was it. Those were the 4 different values we calculated when we calculated each one of those sample variances. Okay, so now let's find the probability of having a sample variance of 0. Well, out of the 9, how many were 0? Well, let's see, here's 1, here's 1, and here's 1. Right? So 3 out of 9 is our probability of 0. So let me see, I think I'll change to another color. Okay, 3 out of 9 probability that we get a 0. How many 2s were there? Okay, Here's a 2. Here's a 2. Looks like there were 2 ways we could get a 2 as our sample variance. 12.5. Here's one. Let's box that one. 12.5 here. 12.5 here. Okay, looks like that's it. So 2 out of 9 there. And finally 24.5. Yeah, here's one. And there's one. 24.5. 2 out of 9. Do a quick check to be sure we've accounted for all possibilities. 2, 4, 6 plus 3. That's 9 over 9 or 1. Good. Okay. So now let's find our x times p of x column. 0 times 3 over 9, well that's 0. 2 times 2 over 9 is 4 over 9. 12.5 times 2 over 9, well that's 25 over 9. And 24.5 times 2 over 9, that's 49 over 9. So the sum of the x times p of x, or the mean of our sample variances, is, this adds up to 4 plus 25 is 29 plus 49 is 78, or approximately 8.67. Again, we get the mean of the sample variances. It's identical to the population variance. So the mean of the sample variance is exactly the same as the population variance. Therefore, the variance is an unbiased estimator. So using the sample variance to estimate the population variance is a very good thing, because it's an unbiased estimator. So it's going to give you good results. But remember, we have a problem with the units. It's often difficult to deal with the variance because the units are squared.